Good afternoon, this is Schweitzer, and we're going to walk through a series of question here, workbook problems, and the goal here is to check your answers. I would also strongly suggest trying these problems and then pause the video and check your answers. Some of them I'll give more detail than others, but in this case we have our first problem, and they want an entropy. I'll try and give a few brief pause here, but give it a try. Obviously, you can pause the video and try it on your own, but either way, here's the answer. We have these three values right here. That one's moved over, but there we go. Pretty straightforward problem here in the sense that we have assigned values on each of these, and you just need to plug them in. So I'm not going to go through. The answer is -200, but so this is for Sn. So it's going to be, in this case, 192. H2 is going to be 131. And then this guy here is 193. This will be times 2. This will be times 3. And this one will be just times 1. Put these all together. That's your total of your reactants, the sum of all your reactants. This is just, this guy would be times the sum of all the products. And of course, products minus reactants equals delta S. Alright, next one. So for this one here, which change describes the delta, the G, change in G as the change in spontaneity reaction as temperature increases. Okay, so again, probably won't remind much beyond this, but you can always pause, try it, and see what you get. For this problem, I see lots of kids solving it and getting the wrong answer, and most of them I suggest you write this out. Alright, and this guy here is given above, right at the top of the problem. You'll see it, and right there, it's negative, it's exothermic. In my mind, I know this is pushing in the spontaneous direction. Alright, we're going to raise this, and this is positive. Now again, we just calculated it right here, but if this problem wasn't there, you still got to note all gases, you're going from 4 gas particles down to 2 gas particles. That's less movement, therefore less disorder. We're losing disorder over the course because we're losing movement. This guy is positive, alright, for more reason than just being, I should say, we're losing. That should be negative. That's what we got here. We're losing disorder, so this guy should be negative, alright, regardless. But a negative times a negative, this whole factor is positive. Alright, combine the two. As this thing gets larger and larger and larger, eventually this guy becomes positive, and the answer is the value increases, which it technically does, and becomes non-spontaneous. Alright, this guy. You know, this interesting problem. It's a good problem. Okay. This problem here, old type problem. Maybe not something you'd see on an AP test these days. This one, yeah, you would definitely see something like this. And something like this, not as much anymore, but this would be definitely in different parts of the test. Alright, so what are we doing here? Again, if you're stuck on this problem, here's a little tip, and you can pause it and try it again. We're warming. We make a phase change. We warm as a liquid. Alright? It's saying that we're going to be completing a phase change. That's the amount of energy required for the phase change. This is the amount of energy to warm per mole. And we have 1 mole. It's nice. A little easier mathematically. Flip the phase. Can require 6010. And then I warm. Alright. Every degree I warm requires 75 joules of energy. Alright. How many degrees am I warming? I'm warming this thing from 0 to 25. So I'm raising it 25 degrees. Every time I raise it to 25 degrees, then I need 75 joules of energy. Alright? Now this is the part where you gotta really start weaving things out and seeing what's going on here. The answer, okay, is going to be C. This is going to be in joules. It's that guy. And then I have this guy right here. Is that energy right there? Next one. Heat of neutralization of a dilute water is that. The quantity of heat per kilojoules, 100 million of this, 3 molar, okay, and 1 molar. Alright, not an easy problem, but it's got a good problem. This is a good problem. First thing I know is that our reaction is H plus OH negative yields H2O. The delta H of this reaction is 60. I'm assuming it'd be negative 60, not that that matters at this point. It just means that it's exothermic. I'm not assuming that I know that. But either way, this is the amount of energy to cycle 1 mole of this, okay, and 1 mole of this to get 1 mole of this, and that much energy. Alright, good problem here. Now again, we always want the delta H is going to be Q per mole. So just fill these two values in. Must use the mole of the limiting reactant. Now you'll note here that we have this same volume, 1 hydroxide, 1 H, okay. This is my, being that I have 300 milliliters here, where is it? 3 molar, okay. This is my excess, so I gotta use this guy here. That's probably the most common error, right? They're not using the right limiting reactant. Alright, so my moles actually is 0.1 moles. And my Q, okay. Because I'm using 0.1 mole, I'm only going to get 1/10 of that energy. 0.1 mole only gives me 6 kilojoules of energy. And that's my answer. Okay. Number 5. Very straightforward reaction. All the following include an increase in entropy except. Okay, increase in entropy means increase in movement. And see here, gas to gas, increase in movement. There's 2 to 1. Liquid to gas, increase in movement. Solid, doesn't say here, probably should have those. That's a gas, that's a solid. Solid plus gas yields solid. This one has a decrease in movement. That's my answer. Alright, the burning of propane. Alright, which the following is true at any temperature. Okay. Alright, well, first of all, burning, this is negative, exothermic. We're going from 6 particles to 7 particles. This is positive. And delta G equals delta H minus temperature times delta S. You'll find that in this case, if this is negative and this is positive, positive times let's see here. So this is positive. So let's just make sure we get this right. Negative here. Is it going to run at all temperatures? Okay. I'm increasing entropy. All right. Or I'm losing disorder. That's important. So I am increasing. Okay. Yeah. I got this right here. So I'll make sure I wrote that down right. Delta H. That's what threw me off. Minus temperature times delta S. You should know that, hopefully. Alright, make sure that's not confusing. This is positive. It's noted right there. Positive and negative is negative. I don't need to go through all this if you realize that this is a spontaneous factor and this is a spontaneous factor. Then this will be spontaneous at all temperatures. Alright, and at all temperatures, that makes that negative. Now be careful when you look at this. H is less than 0. Yes. Bigger than 0. Yes. Less than 0. Yes. Therefore, all 3, 1, 2, and 3, that's my answer. Alright. This one here. Old style question. Okay. And doesn't really do much for us other than understanding how some things work under the hood. When I have a delta H of formation and sum of the delta H formation minus the sum of the delta H of formation of the products minus the reactants to give me a delta H, well then technically on the hood these formation equations are being used. And which of these is the standard formation of barium sulfate from elements? So we got to have some idea of the elemental form of these things that someone just designated. And in this case, that's a solubility thing. Okay, this is it right there. These are the standard forms. If you look on your delta H formation tables, you'll get 0 on all of these guys. Right? All right. On this one. Okay, a couple things here. At 25 degrees Celsius, you should be aware, as being present on Earth for a while, that this will happen as ice melts at room temperature. So this is negative. It is cold. This is positive. And we're increasing movement, so it's positive. All right. So less than 0. Okay. These guys out. If it was actually at 273, that would be a good question here, because then this would be one of the two. I like that. I like that answer. My question a little better. Either way, positive. Okay, so of these three, greater than 0, so this guy's out. And then positive, so we're down to these two. And therefore, that's the answer. A cube of ice is added to some hot water in a rigid container, insulated, and then sealed. There is no heat exchange from the surroundings. What happens to the total energy of the system and the total entropy of the system? Okay, so energy. Because it's in an insulated, they're making the premise that this is going to be the option here. These guys are out. And because we're going from a solid to a liquid, we're increasing movement over the course, so we have essentially a container where we have some water, which is hot, and you drop an ice cube in. Either way, we're going from having water in a solid, a liquid, and a solid, to just having a liquid. That being said, we're increasing in movement. So, there it is. C is the answer. This value is negative for any exothermic reaction. Pretty easy, too low level, either way. Gotta have some of those, I guess. Alright, 11 grams of this stuff. So we have, just note here, whenever I see that, a few things you might want to note, that's about 0.1 moles, roughly. Okay. Compound dissolved in 100 milliliters of water, so that's 0.1 liters. So just a side note, that means we have 1 mole per liter. Dropping 10 degrees. Which of the following represents the net ionic equation dissolved? Okay. Just dissolving net ionic. That one doesn't have ions. Out. This guy is nothing. This guy is... that's the hydrolysis equation of the... not even the correct... it's out. This is my answer. Okay. Next. Alright, same thing. Now again, how many calories are transferred in this process? Okay, well, first things first, dropping 10 degrees. Okay. The definition of a calorie is what they're going off of here, that it takes 1 calorie for every 1 gram of water or milliliter, assuming density is 1, to change it 1 degree Celsius. So you could use this Q equals mass times change in temperature times specific heat. Mass is 100, change in temperature is 10, specific heat for water is 1 if using calories, and therefore the answer is 1,000. Same problem, which the following shows the enthalpy. Okay, so it's going to be Q per mole. All right, that's going to be Q, which is going to be the previous question, 1,000, divided by the number of moles, which I mentioned just a minute ago, is 0.1. All right, and that's my answer. Now, they could just have had this as being answered as being 10,000 calories, but this one's out. It's not the right. This one's not good. This one is nothing. This one here, okay, they're making a little jump here from 1,000. 4.18 is my conversion to joules. So this one actually is correct. All right, same deal here. All right, what are we doing here? Well, what are we breaking? All of bonding is delta H is equal to the bonds broken minus bonds formed. So it's always important to note what's being broken. Here, we're breaking an ionic bond, and we're forming a dissolved substance, which forms an ion dipole. Okay. Now, whenever I break bonds, energy has to be put in. Energy enter. Okay. That anything we have to invest energy, we typically call it endothermic. And when any bonds are formed, you get energy back. That's exothermic. Now, the size of those two ends up being whether you end up being exothermic or endothermic. But so ionic and ion dipole. Looking for endo. So ionic endo and ion dipole exothermic. Good question. Good question. All right, so we got a series of problems here, and they want this guy. All right, think about this for a moment and say, okay, what do I need here? Okay, this guy is going to be a Hess's law problem, and all right, so I like this problem. I think this is a little bit older style of way of doing it, but it's got some good Hess's law stuff in here. So again, let's walk through how we would solve this problem. I may not give the answer to this one. You can try it on your own. But in this situation, okay, first thing, check reactants products. Okay, that's a reactant, that's a product there, so I have to flip this one. And that's going to be a plus 104. All right, and then this guy's a carbon. That's not in here. Okay, but now this guy got flipped. So it is using intermediate, this thing could cancel. Carbon dioxide is a product, and it's a product here, but there's 3 of them here, and there's only 1 here, so times 3. I don't have a calculator. I could punch it out. Not that it matters. Okay, we'll leave it. And it's going to be negative. All right, and then this guy again is not in the problem, so you could check canceling intermediates. But I have water here. Water is a product. I got 1. I need this thing times 4. All right, and at that point, simply going to add everything together, and you can check to see which of these guys algebraically would give you the correct answer. And I had to check that one out to see what we got. And at this point, I'll let you figure that out. Okay. So it says a reaction mixture here is set up using a 1 molar concentration of all the chemical reactions. The reaction is both exothermic and exergonic. This means I have a negative delta H and a negative delta G. Alright, this following is true. Now again, a couple things here. Delta G equals delta H minus temperature times delta S. This guy is negative. Okay, that means, because this is spontaneous, that we got a spontaneous here, that the sign of delta S could be either, depending on the temperature. If it is going to be positive, then this temperature just doesn't matter. If it's negative, then the temperature matters. But let's look here. We got ourselves a aqueous and a solid. We got all aqueous. We're gaining movement. This guy's positive. So we got this situation here. The temperature doesn't matter. Okay. All right. So we got 1 molar concentrations of everything, of all things. So not the solid, obviously, but 1 and 1. Alright, the reaction has both axial. Okay, so start off, just so you know, if everything's 1, 1, 1, plug it into the equilibrium expression, and it should be 1 to start. This guy is out. Be 1 over 1. The reaction quotient will increase to become K. Alright, so in this case, we're going to drive towards products. It is a ratio of products over reactants. That's my K value, eventual K value. And I'm going to go this way towards products, which means that I'm going to be getting bigger, and that my K value is going to be larger than 1. And since I'm at 1, and I'm going to be bigger than 1, then the reaction quotient will increase to become K. Yes. The driving force in the reaction is enthalpy only, not entropy. That's false. It's 2 only. Which of the following relationship represents the first law of thermodynamics in a system? So this is one pretty common question, way past, but in a sense here, whatever the system. So it says first, axial thermic. Okay, that's an important term right here. Means where our system is going to be likely losing energy, and we're gaining energy surrounding, and nothing else really matches up here. Alright, one version of the second law of thermodynamics for a spontaneous process includes this. Okay, and I don't know that I always talk about this enough, but essentially the second law of thermodynamics just says that in the end, okay, if you have a system and you have a surroundings, for any reaction that happens, that unlike the conservation of energy, means that the two would match. They're saying that if you add the two up, it's always going to be positive. And we're gaining bigger than 1, bigger than 0. So, for any spontaneous process. Okay, so which of these matches that idea? Take a second. I believe, in my point of view, this guy. Alright. Next one. Okay. Really good question here. Obviously, take a second, try it out. Alright, so you should be able to actually calculate this out here. So we got 430, and then no calculator here. Alright, this guy is 240, and this is 2 of them, which is going to be 430 times 2, which is going to be 860. Broken minus formed is going to put those together, and 40 at 70 plus 670. Okay, so we have 670 minus 860. Okay, now again, do a little chicken scratch there, and we got negative 190. You should note that will be negative, so it's okay. Negative 190. Alright, so it's exothermic. Again, if you didn't get that far, take a look. Which of these would match up here? Looking for an exothermic graph of delta H of 190. Exothermic, 190. There we go. And we'll stop there. I think that's the end. Okay. Thank you very much.